Okay, we're into part 3, which is the pulse duration modulation driving system. Specifically, we're going to be using the TL494 chip that we've rescued out of the ATX power supply. I'll be going through this chip in detail so we understand how it works. I've added the 494 pulse width modulation chip to the board. Again, I'm having a heck of a time trying to deal with the perf board construction, and it did take a while to buzz it out and make sure everything was working. So let's look at this modulator and see what it's all about. Okay, come on, everybody loves the 741. I mean, you can't even walk across the shack without having your foot impaled by a upside down 741. So, plenty of gain here, plenty of gain bandwidth for an audio amplifier, and all we're doing is amplifying the electret microphone and bringing it up to the level that we might drive the TL494 pulse width modulator. So, with a microphone amplifier like this, we need to have some gain, but not too much. So I'm going to start with a 1K resistor on the inverting input and a 100K feedback resistor. So that's a gain of 100. Log of 100 is 2 times 20 would give a gain of 40 dB. Now, I'm not sure if we're approaching 40 dB, but that's the amount of gain that the op-amp is supposed to give you, probably in the middle of the audio range. I've got two capacitors that we can play with. We have the input coupling capacitor. The input is defined by the 1K resistor. This is a virtual ground, so it's exactly a 1K input on this op-amp. So we can, knowing that our source is fairly low impedance as well, we can calculate this capacitor and come up with a low frequency cutoff frequency, a low cutoff frequency, and I found that a 0.47 or a 1 mic gets you well below the audio range into, you know, the 30, 40, 50 hertz region. We can measure that and see where we ended up. Also, putting a capacitor in the feedback allows you to shape the high side, and we can get our 3 dB point or 6 dB point if you want situated. I don't want to have a really wide transmitter, so I'm going to try to have my 3 dB point around 5 kilohertz. I think that's reasonable. And you'll notice I've got a 1K resistor nailed onto the output of the amplifier. Remember, we're making 6 volts here, so there will be 6 volts there. And you're saying I'm shorting that 6 volts with a 1K potentiometer. No real problem there. It's just a few milliamps of wasted power into the resistor. You can always insert a capacitor here if you want to. So, anything else interesting in this circuit? Here's the electret. We've got a nicely bypassed power supply. The voltage is going to be developed across this 1K, and it's going to go right into the op-amp. I think this is going to be excess gain, actually, but I wanted to start with a decent amount of gain. And I have a 1K pot. Everything's low impedance in this circuit, so it doesn't pick up a lot of noise. Also, when you're using a test signal, you want to have a good solid output, but you don't want to be in clipping with the amplifier. So I figured about 10 millivolts RMS on the input was a good place to start. And with 10 millivolts RMS, you know, we should be able to get something like 1 volt RMS out. So let's take a look at the scope and see if we have a nice sine wave. We do. So we're not overdriving the amplifier. And let's look at the RMS voltmeter. And let's see if we can connect to the RMS voltmeter. Okay, so it looks like that's pretty much already set for 1 volt RMS output. and I'm at 1K, 1K, 1000 hertz for my test signal. And looking over here at the input, looks like I got about 12 millivolts RMS. So it's not quite 40 dB of gain. It's probably around 35, 36 dB of gain. But again, that's plenty for the audio range. Okay, I have now attached the bias to the input of the microphone amplifier. So we now have the connection from here to here made, and the connection from here to here. The microphone is now connected. So we're still on the 1 volt RMS scale. Let's go up to the meter. Up to the meter, 1, 2. I'm talking into the microphone. Hello, 1, 2, 3, 4. Hello, 1, 2, 3, 4. This is the 1 volt RMS scale. Looks like we did pretty well with our estimate. We're not overdriving. We're definitely in the linear range on the op amp. And of course we have that output control on the schematic that will allow us to adjust this down accordingly. Now if it turns out that it's gross and it's way too high, we can change that feedback resistor on the 741 to something smaller, like a 39K or a 47K, to cut the gain down. But good estimate on the electret microphone. We now have our microphone amplifier and it is working. Now, as a critical test, I have put a pair of headphones on the output of the amplifier to listen to the noise that is generated by the circuit with and without an input. And I substituted a different op amp for the 741. I put it in op 37. The op 27, op 37 would both be appropriate. These are low noise bipolar op amps. And I did notice quite a difference in listening to the background noise. I didn't notice any difference in the fidelity, and probably as a microphone amplifier it wouldn't make much difference. But I did want to note that using a lower noise op amp is a real thing. The 741, of course, is not a low noise op amp. It's a very early type op amp circuit. But noticeable noise reduction using a more modern operational amplifier. That's just a note. So let's talk a little bit about the TL494 and Pulse Duration Modulation. Now, as you know, you can certainly represent a sine wave very effectively using PDM. And we can see in this diagram that we can go positive and we can go negative. That's going to be very important when we're doing modulation, AM modulation. We need to have upward and downward swing. And we're going to have to handle negative peaks as we get closer to the modulator section. You'll see how we handle that. I've gone back to the original diagram, and we have some features I want to talk about now. There are 46 active transistors and many diode connected junctions. We have a supply voltage that works up to 42 volts DC. There's 2 op-amp error amplifiers. There's a Brokaw band gap reference regulator. The output can be set to push-pull or single-ended operation. There's a dead time control. Grounded is shortest with the dead time control. We have an on-chip oscillator and sawtooth generator. Frequency programmable by a resistor and capacitor. There's an internal PWM comparator. The chip really has more than we need for a complete PDM generator. The output pulse varies from about 97% of the period to 0 as the voltage present at the amplifier, the error amplifier. Output varies from about 0.5 to 3.5 volts. So for full pulse output control,
we need about a 3.5 minus 5 times 0.707 volt RMS, or about 2 volts of audio. 2 volts RMS of audio to move this thing up and down and get a 0 to about 97% duty cycle on the PDM. So on board we have some interesting things. We have a couple of operational amplifiers. They're called error amplifiers, and we don't actually use both of them for our modulator. We're only going to be using one of them. There's an oscillator that produces a sawtooth waveform, which is the heart of the pulse width modulator. The pulse width modulator is a comparator circuit. The comparator compares the analog input that we're putting in through this amplifier with the sawtooth wave, and it produces the pulse duration modulator at this point. Now, why do we need all this circuit if we've already got PDM here? And the answer is this clever little flip-flop that they've added, which is output control. And output control allows the device to either do single-ended with both devices in parallel if you want, or they can be in antiphase so that one goes up and the other goes down. And this is useful for driving different types of converters and power supplies mostly, or with audio amplifiers perhaps. There's also an onboard Brokaw bandgap reference. It's a 5-volt regulator. So we've got all of these features. There is a dead time control comparator that we simply ground so that it is at its fastest speed. We can get into that a little bit later, but essentially we just ground this point, the dead time control comparator. We want to make sure that we have no dead time between the pulses. We want them switching as rapidly as possible. So here's the timing diagram. It's a little bit busy, but you can see where we have the sawtooth wave, and we have a voltage input which produces different pulse durations depending on the amplitude against the sawtooth wave. The rest of this is just devoted to whether the control output is set for antiphase or for both transistor outputs to be in phase, as we see here. So here is a functional block diagram. The functional block diagram shows roughly how we're going to connect the pins on the IC. First, we have a resistor and a capacitor that form our RC time constant. Basically, you can estimate the frequency of the sawtooth waveform by taking 1 over the product of R times C. The audio input is going through a small aliasing filter. Remember, we put some low-pass filtering in our microphone amplifier. We're adding another pole here, and this is going to just make life easier by filtering out all of the audio components from getting involved with our 60 kilohertz oscillator that we're running here. We want to make sure that we're just putting the audio into the comparator and not putting harmonics or noise at high frequencies into the comparator that will cause distortion. Now, in order to modulate into the error amplifier, we have to have a voltage that sets us basically at the 50% duty cycle to start. And we do that with this potentiometer here that's taking the 5-volt reference, and it's putting it at a point where we get a 50% duty cycle. Then as we put the audio in, speech, we cause that voltage to go up and down, and thus the comparator gives us the different duty cycles at this point. Again, the rest of this is just making sure that either the output is antiphase here, output, or they're both in phase. If we ground the control, they're both in phase. So each of these has approximately 250 milliamps of capacity. by putting them both in parallel, we actually have almost a half an amp that we can source with this system. We are going to be sending this into a pulse width modulator driver. It's a complementary symmetry emitter followers, a PMP and an NPN. They're external to the chip. So I think that describes pretty much the whole chip. Here's the output control pin. Grounded, we get the single-ended PWM. And once we tie the control pin to reference, or the 5 volts, we put them in antiphase. Q and Q naught become active. However, remember, it's a flip-flop, and flip-flops divide your frequency in half. So we'll now have to raise our sawtooth wave from 60 kilohertz, where I'm running it, to 120 kilohertz to get the same effect. Finally, let's look at the duty cycle, or mark space ratio. That's an old-fashioned term. You're used to this now. You can see how varying the voltage changes the pulse duration. But where do we want to set the PWM duty cycle at rest? In other words, when you're not speaking into the microphone, what is the duty cycle of the PWM? And the answer is 50%. 50% duty cycle. 10% duty cycle, 90% duty cycle, and it all has to do with the percentage of the reference voltage that we're presenting to the input error amplifier.
So when you're pulling transistors off these ATX power supplies, you're going to find some pretty nice devices that are made for driver service in the hundreds of kilohertz region for these power supplies. And sometimes you'll find complementary pairs that are well matched to be used for complementary drivers. And I pulled off a few transistors. Turns out these three are PNPs, and this is an NPN. This is a PNP that happened to be complementary. The NPN is a 2SC1815. It's a 50 volt part, and it has impressive power, and should be excellent. And I found its complement on another ATX power supply, and that's the 2SA1015. So these transistors were made to be put in complementary symmetry driver stages. They have almost identical FT, and I'm going to use them rather than, using a 2N3906, 2N3904 type thing. I'm going to use the transistors that are actually off these boards that are actually designed specifically for driver service. So you may have a question on where we're supposed to set the resting duty cycle. And it turns out that for AM modulation, similar to a Class D kind of a audio amplifier, you want to set it for approximately 50% duty cycle, or 50% mark space if you're old-fashioned. So once we've got this set up for about 50%, 1, 2, 3, 4, now you can see the modulation occurring on the waveform. Also, I put the 741, or actually another 741 in. There's really no problem using the 741 as a microphone amplifier. That little noise experiment was simply, simply something to do to pass time. When you've got an op amp that you can stick into the socket with no modifications, of course you're going to try it, right? So here we are, the Pulse Duration Modulator set up for AM modulation, and it's ready to now drive a MOSFET. So next I want to do an end-to-end distortion test through our Pulse Duration Modulator. Basically what we have here is we're taking the generator straight into the distortion analyzer, and I'm measuring less than 0.1% distortion. So the generator is acceptable. I'm lowering the value on the generator to around 10 millivolts, putting it into the mic amp that's on our board. Goes into the Pulse Duration Modulator, where we get the variable pulse wave that represents the 1 kilohertz input. Then I want to demodulate it and try to get the sine wave back. And that involves a filter. I've tried a 1-pole, a 2-pole, and a 3-pole. With a 2-pole, I was able to get the distortion down to around 2.5%, which is not bad. But with a 3-pole, I'm doing better. On the distortion analyzer, I'm on the 1% scale, and I'm hovering around 0.3, 0.4 for distortion. Now this instrument's old, it's uncalibrated, so I still consider this kind of a relative measurement, but it does show that I'm able to encode and demodulate through the whole system on the board and not produce any more than around 0.35 to 0.4% distortion. So this pulse duration modulator using the TL494, even though it's fairly simple, it's doing a pretty good job. So this is a great starting point for a pulse duration modulator transmitter. Okay, so next time we get to the higher power part of this, we're going to be working on some filters. We can't be putting square waves into our circuit. We have to be able to filter things out so that we separate the actual modulation audio from all of these sharp pulses that we've been generating. Plus, we need to start looking at the final amplifier. We're going to try for a Class E style amplifier. We completed the RF driver in the second video. So stand by for the fourth video where we get into the higher power section.